All right, guys, looks like the quiz is timed out. So let's go ahead and get started with today's notes. All right, so what I want to do today is basically pull together a few last minute concepts that we have to think about when we're dealing with the ideal gas equation. So we've kind of looked at some applications of that and how we might use the ideal gas equation. And then there are a few other little things that come into play here that are going to help us to expand that out a little bit, especially as we move into the next topic, which is called eudiometry, which is the topic of actually Friday's video. And that's collection of a gas over a liquid in order to quantify the amount of gas that's there. And I think you guys actually do a eudiometry experiment in the lab as well. So we're kind of putting together just a few more concepts that'll be useful in that direction. So the first one is sort of a shortcut type thing that you see a lot in some of the Chem 101 problems, and that's this business of standard molar volume. Okay, so what this corresponds to is the volume of 1 mole of gas taken under what we call standard conditions. So when we talk about standard conditions, what we're really talking about is the standard temperature and pressure. So what those turn out to be is the standard pressure is 1 atmosphere, and the standard temperature is 273.15 kelvins, okay? So whenever we see these two numbers, we consider this to be STP, or standard temperature and pressure. So a lot of times in the Chem 101 problems, they'll say, assume a gas is at STP. And what that means is standard temperature and pressure. So we're talking about a pressure of 1 atmosphere and a temperature of 273.15 Kelvin. So we're nailing down those two variables basically. So what we want to do is figure out what this so-called standard molar volume is. It's that volume that's 1 mole of the gas is going to occupy under those conditions of temperature and pressure. So we can do it quite simply by just using the ideal gas equation. So we can say PV equals N times R times T, and I want to solve that for volume, right? So volume is N times R times T divided by P. All right, now let's stick the variables in that we know. And I'm going to do it in terms of liter atmospheres per mole Kelvin. Your book would do it, or Chem 101 would do it in terms of bars. Remember that bars and atmospheres are more or less interchangeable, but keeping in mind that the gas constant changes just a little bit if you use bars, but you basically get the same answer. Okay, so N is going to be 1 mole of my gas. R is 0.08206 liter atmospheres per mole Kelvin. All right, and temperature is 273.15 kelvins. All right, and then we got to put that over a pressure, don't we? And that pressure is going to be 1 atmosphere. All right, so when we work all this out, and of course we should get volume units out of this. So atmospheres cancel with atmospheres, kelvins with kelvins, moles with moles, and we get liters out. And when you work this out, what you're going to get is 22.4 liters. Okay, so this is true for any gas as long as it's under standard conditions and we consider it to be an ideal gas. Now we'll come back probably next time when we talk about collision theory and talk about what we really mean by an ideal gas as opposed to a real gas. And we'll get to that a little bit later, but assume this is true for an ideal gas. Now, this again is the volume taken up by 1 mole of an ideal gas under standard temperature and pressure conditions. So it's kind of a shortcut. So for example, if they give you a problem that involves a volume and tells you that you're at STP, well, then you know you're at 22.4 liters. You don't have to go back into the ideal gas equation and go figure that out. So you can use that as a starting point, for example, in a problem. So it cuts down the number of steps that you have to do. So that's basically why we look at it. It's kind of a benchmark for volume for an ideal gas. Okay, any questions about that? And you'll see problems in Chem 101. I think, matter of fact, there's 1 or 2 in today's practice that involve this as well. Everybody okay with that? Okay, good. Now, the next useful thing that we have to think about is this thing called Dalton's law of partial pressures. And this is going to be a law that applies to gaseous mixtures. All right. So keep in mind, air, for example, is a mixture of gases. It's not just one gas, right? It's going to be oxygen gas, nitrogen gas, there's a little bit of helium, carbon dioxide, a little bit of methane, a whole bunch of things in air. Okay, so really, if we talk about the pressure of air, we could really talk about it as being the combined pressures of all those different gaseous components that we have in the mixture. And that's really all that Dalton's law says. Okay, so what it says is that the total pressure of a mixture of gases is going to be the sum of the pressures of the individual components of the gases. Okay, so it could be pressure for component A plus the pressure from component B plus the pressure from component C. And then we could add that as many terms as we need to, we'll say up to P sub X. Basically for how many components we actually have in the gas. And these pressures, by the way, that we add up are considered to be what we call partial pressures. And the reason why we call them this is because when we add them up, we get the total pressure, right? So we add all the partial pressures of the individual components together, and we end up getting the total pressure of the gas, okay? That's all Dalton's law says. Now, what we can do is apply this to an example or two and just see how it might work. All right, so here's a simple example that applies Dalton's law of partial pressures here. So let's read through it here. It says here that we've got a gas cylinder. It's got a volume of 53.7 liters, and it contains nitrogen gas at a pressure of 28.2 atmospheres and a temperature of 26 degrees Celsius. So the question now is how many grams of neon gas, okay, different gas now, do we have to add to this tank, okay, to raise the total pressure up to 75 atmospheres? And that makes sense, right? If I add a new gas to the nitrogen that I've got in there, the two gas pressures have to add to get me to a total pressure of 75 atmospheres. So that's kind of my starting point for the problem. Okay, and ultimately I need to be able to work backwards to the amount of neon gas that I'm going to need for that to happen. Okay, so let's go back to Dalton's law here. We know that P total, in our case, how many different components do I have here? Anybody catch that? How many different gaseous components do I have? 1, 2, 3, how many? Two. Yeah, you got it. We got the nitrogen and the neon. So that means I need two components. Good. So I need the partial pressure of the nitrogen gas plus the partial pressure of the neon gas. Now the neon is what I'm being asked for, right? So what I can do here, because I have the total pressure I'm shooting for, and I have the initial pressure of the nitrogen, I can solve for the pressure of the neon, can't I? So that just turns out to be P total. That's what we're shooting for, minus the partial pressure of the nitrogen gas, which we're also given. Okay, so if I work that out, that turns out to be the 75.0 atmospheres. That's the total pressure once I add both components. I'm going to subtract that from that, the nitrogen pressure, which is what, 28.2 atmospheres. Yeah. And when I work that out, I know that I have to add enough neon to supply a pressure of 46.8 atmospheres. Okay, so in other words, I've got the partial pressure of the neon now. Okay, so now what I'm asked to do is to figure out, okay, how many grams of neon gas am I going to need to supply that partial pressure? So I need to relate the pressure back to an amount of gas, okay, at a certain volume and temperature. Do I have an equation that lets me do that? How would I get from the pressure of the neon back to, let's say, the moles of the neon? Because once I have the moles of the neon, I can get the grams of the neon. Okay, so what's a go-to equation I could use for that? How about PV equals nRT, right? I've got everything I need. So we can go to that situation. All right, so what am I after? I'm after N. I want the number of moles of the gas, right? So N is going to be pressure times volume divided by R times T, PV over RT. All right, let's go ahead and add in what we have, make sure our units are good. All right, so the pressure here is for the neon. That's what I'm after. So that's the 46.8 atmospheres, right? I need the volume. Okay, that's already in liters. That's good. Okay, so that's 53.7 liters. That's defined by the volume of the tank, right? And R, 0.08206 liter atmospheres per mole Kelvin. And then I need times the T. Oh, I'm in 26 degrees Celsius, but what do I need to do? I got to convert that to Kelvin, don't I? So let's go off to the side and do that. So I've got 26 degrees Celsius, and I get to Kelvin by adding 273, or if you want, 273.15. And you get 299 Kelvin. So we'll put that down here. All right. So now when you work all this out, the calculator tells me that I'm going to get 102.4277. Okay, and what's that going to be? Should be moles, right? All right, so let's make sure we did this right. Atmosphere should cancel with atmospheres, liter with liters, kelvins with kelvins. Oh, look, the moles are in the bottom of the bottom, so they go to the top. Okay, and what kind of sig figs are we looking at here? I think we're talking about 3 sig figs. All right, so now what am I going to do? I want a mass, don't I? So really, all I have to do at this point is use the molar mass of neon to get me from moles to grams. So I know that 1 mole of neon corresponds to a mass of 20. This is from the periodic table, 20.1797. That's grams of neon. Okay, so that takes moles out of the equation, leaves me with grams. And to 3 sig figs, you end up getting 2.07 times 10 to the third grams of neon. Okay, so that's a nice application of Dalton's law of partial pressures along with the ideal gas equation. So everybody, does it make sense to everybody what we did here? Now I'll go back in case anybody still needs to get that problem down. Everybody good? All right, let's look at one more problem then. So this one is a little bit different. And it's asking here, what is the partial pressure of chlorine gas in terms of millimeters of mercury at 0 degrees Celsius and 1 atmosphere of total pressure in a gaseous mixture consisting of 46.5% nitrogen? That should be an N2 there, shouldn't it? I don't know why I left my 2 out. 12.7% neon and 40.8% Cl2 or chlorine gas, all by mass. Okay, so I'm looking at this, and this is kind of a Dalton's law problem when I think about it. So what it's really asking me to do is to pull out a partial pressure of 1 component out of a mixture of 3 different gases that are there in different amounts. Okay, that's essentially what the problem's asking me to do. So the first thing I'm going to do is I'm going to take all of those percents by mass and I'm going to get them over to moles. Now this kind of looks a lot like an empirical formula problem that you guys saw a while back, right? So when we talk about percents by mass and we want to get them to moles, what's the easiest way to do it? Well, the easiest way to do it is to assume I've got 100 grams total. Okay, so we're going to work it kind of like an empirical formula problem, at least at the outset. So let's go ahead and write down our percents by mass. If we assume 100 grams, well, then those percents by mass just turn into grams, don't they? So I've got, just writing it down, 46.5 grams of nitrogen gas. I've got, what, 12.7 grams now of neon gas, and I got 40.8 grams of chlorine gas. Now what I'm going to do is convert each one of those to moles, okay? Why? Because our gas law equations don't have grams in them, but we do have gas law equations that put things in terms of moles, so that makes sense to do. All right, so let's do that. Using our molar masses from the periodic table, know that 1 mole of nitrogen gas is 28.013 grams of nitrogen gas. And that turns out to be 1.6599 moles of N2. And we'll just keep track of our sig figs as we go. We know that's good to 3 sig figs, so I'll underline those. Do the same for neon. You know that 1 mole of neon gas has a mass of 20.1797. That's grams of neon. And if you work that out, that's 0.6293. That's moles of neon. And again, watching our sig figs, we're good to 3 there. And then finally, we can do chlorine gas. Okay, 1 mole of chlorine gas, according to the periodic table, has a mass of 70.906 grams of Cl2. Okay, and what we'll end up with here is 0.5794 moles of Cl2. And in terms of sig figs, we're good to 3. All right, so the deal here is that, again, I'm trying to make a comparison now. It's kind of almost an initial final type situation, if I wanted to think of it as that, between the total mixture of the gas, all the gases together, and then one specific gas, which is the chlorine gas, okay? So what I need to do is I need to first sum up the total number of moles of gas that I've got. So I'm just going to add those up. And what I get is 2.8646 moles total of gas. Okay. And it looks like I'm going to be good to the hundredths place there when I add. So I've got essentially 2.86 moles of total gas to sig figs. So now, what is it that I'm trying to relate? Let's just go back and remind ourselves of what we're trying to do in the problem here. All right, I'm trying to get the partial pressure of the chlorine gas. Okay, that's what I'm after. All right, now I'm at a set temperature, okay, and I'm at a set total pressure. Other thing I have here is a total pressure, okay? So that's the pressure applied by all 3 of the gases mixed together, according to Dalton's law of partial pressures. All right, so that being said, do I need to worry about volume? No, it doesn't say anything about volume in here, so I'm going to assume that volume is constant, right? Do I need to worry about temperature? No, I don't, because temperature is also held constant here. So really, what am I trying to relate? I'm trying to relate pressures to number of moles of gas at constant temperature and volume. What law does that for me? I can use a simple gas law here. Okay, which gas law do I want to use? What's the one that relates pressure and number of moles? Anybody remember?
Avogadro's.
You got it. Okay, so we want to use Avogadro's law. Now remember what it says. It says that pressure is proportional to the number of moles of gas at constant V and T. Okay? What was another way of writing that? Remember, we could kind of say that the pressure is equal to a constant K times n, and then what we could do is we could solve for the constant. So the constant is p divided by n, right? So now remember, I could set that up as a set of initial and final conditions. So I could say p initial n initial is equal to p final over n final. Okay, so that's my useful variation of this. But now what I want to do is set these initial and final situations up so I can relate them just like this. All right, so I could say, for example, that the pressure of the Cl2 divided by the n of the Cl2, and it doesn't matter which one I set as initial and final, is equal to P total, which is for the total mixture, divided by n total. Okay, so what do I want to solve for here? Well, I want to solve for the number of moles. Was it the pressure or the number of moles? I think it's the number of, is it pressure I want? I think it's pressure I want. Yeah, isn't that what the question asked for? What's the partial pressure? Yeah, so I want P. So this is what I'm after. I want the pressure of the Cl2, okay? So now let's go ahead and solve the equation for that. So that's going to equal to number of moles of Cl2 times the P total divided by the n total. Now, do I have all those things? I think I do. I think I do. Do I have the number of moles of the Cl2? Yeah, I got that. Do I have the total pressure? Yeah, that's given in the problem. That's 1 atmosphere. Okay, do I have the total number of moles? Oh yeah, I just figured that out here just a minute ago. Okay, so we have everything we need. So let's go ahead and plug everything into the equation here. Number of moles of Cl2, let's go back up and look. That is 0.5794. What do we say to sig figs? I think there were 3 in that. And that's moles of Cl2. Okay, and I'm going to multiply that by P total. We said that was 1 atmosphere, right? That was in the problem. And we want to divide that by n total. Oh yeah, where did n total come from? Oh yeah, that was the total moles of gas we just summed up. 2.8646. And that should be in terms of moles of gas, right? All right, so it was 2.86 there to 3 sig figs. So what's going to happen is moles will cancel with moles, we'll be left with atmospheres here, and that's what we're trying to get. So turns out the partial pressure of the Cl2 in terms of atmospheres is 0.20087. And that's atmospheres of chlorine gas. Okay, and we are good to what? 3 sig figs on that. Now, also, we wanted this in millimeters of mercury, didn't we? So I have to do one more little conversion here to get me to millimeters of mercury. So I know that 1 atmosphere is equal to what? How many? 760 millimeters of mercury, is that right? I think that's right. Okay, so atmospheres cancel with atmospheres. We'll be left with millimeters of mercury. So I end up getting to 3 sig figs, 153 millimeters of mercury. Okay, so this is another nice application of Dalton's law of partial pressures here. All right, and I was also able to kind of slip a simple gas law in here as well by, again, looking at what the problem is asking me to relate and looking at what other variables are being held constant. All right, any questions about that before we do a little practice? All right, so let's open up some Chem 101 here, guys. All right, going back to in-class exercises, we want chapter 9, and we are going to do applications of the ideal gas equation. Okay, so it's about 15 minutes, and that's exactly the amount of time we have left in class. So that timed out nicely, guys. Looks like you got, what, 4 problems to work? Oh, and there's an STP one in there too, so that's good. All right.
Dr. Richardson, could you go over
Sure.
the unknown sulfur oxide one?
Yeah, the last one. Yep.
Thank you.
What did you ask about it? I think I missed it there.
So can we go over the
Yeah,
unknown sulfur oxide one?
Yeah, sure can. So if you think about this, they're asking for a chemical formula. So you want to know if it's SO2, SO3, SO4, whatever the case may be. So it's the number of oxygens that can vary. So what important piece of information can you get out of a question like this that will let you figure that out? In other words, from the gas information that's given there, what could you determine that'll help you figure that out? It was one of the things we did in the video last night. How about a molar mass, right? A molecular weight. If I had an experimental molecular weight, in other words, I knew how many grams per mole of the stuff that I had, then I could pretty much go back and figure out how many oxygens are in there, right? By just starting to add oxygens in until I hit that molar mass. So could you get a molar mass? That's really kind of the basis of the problem. Could you actually get a molar mass out of the information that's given there? So we just looked at it real quick. And I didn't want to write for some reason. There we go. So molecular weight is in terms of grams of the gas per mole of the gas, right? Do I have the grams of the gas? Yeah, I do. That's 1.636. Okay, so I got the grams part. I just need the moles part. Okay, so how do you think I'd get the moles part? Well, probably using PV equals nRT, right? So we can solve that for N. That's the number of moles. That's going to be PV over RT. Okay, and then you've got a pressure, don't you? Yeah, you got 1 atmosphere of pressure. Do you have a volume? Yeah, you got a volume. You know what R is. Do you have a T? Yeah, you got a T. You got to convert it to Kelvin, so you're good to go. So once you have the moles, then that gets stuck right back in there. So you got the grams, you got the moles, you got the molecular weight, and you're good to go. Does that help?
Yeah, thank you.
Sure, no problem. So just a few more things to mention as we finish up, guys. Make sure you look at the new video for Friday, which I think is the udiometry video. And be ready for a normal Friday quiz. So that's going to be all on gas law stuff. And by the way, I'll remind you guys again, but I've got my vaccination appointment next Monday to get my COVID shot. So I'm going to give you guys the day off on Monday because my vaccination happens to be right at class time. So you guys get the day off on Monday, but I'll remind you that on Friday. All right, guys, any other questions?